Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at some strategies for doing integrals involving other trig forms. Before we take a look at any examples, I want to review some trig identities that we've talked about in previous videos. These are the Pythagorean identities: cos squared x plus sine squared x equals 1, 1 plus tangent squared x equals secant squared x, and cotangent squared x plus 1 equals cosecant squared x. In addition, we have two double angle identities: cos of 2x equals this and this. But what I like to do is rearrange both of these so that I can isolate the sine squared x and the cos squared x. And you'll see why I'm doing that once we get into the examples. So this first one, I'm going to isolate this term. So I'm going to have 2 sine squared x will equal 1 minus cos 2x. I just move this term over this side, this term over this side, and then I'm going to divide by 2. And I divide each term by 2. So you're going to see that this is very useful when we're doing some of these integration questions. I'm going to do the same thing here. I'm going to isolate cos squared. So I'll first of all isolate 2 cos squared x, and that will equal 1 plus cos 2x. Divide by 2, so cos squared x will equal 1/2 plus 1/2 cos 2x. Those two identities are going to be very useful in some of these examples. Let's take a look. In our first example, we have sine squared 3x. If I had a cos of 3x, I would be able to integrate this according to my power rule, because I'd have u to the n and I'd have my du factor. However, I don't have that cos of 3x factor. So what I'm going to do is I'm going to replace this with that double angle identity. So instead of sine squared 3x, I'm going to replace that with 1/2 minus 1/2 cos of 6x dx. Now I'm going to break up these terms. So that will be integral of 1/2 dx minus, I can pull that 1/2 out if we want, cos of 6x dx. The integral of 1/2 dx is simply 1/2 x. Now, in order to integrate this term, I have cos of 6x. I can use my cos of u pattern, but I need a 6 as a du factor. So I multiply by 6 and I also divide by 6. So now I have the pattern cos of u. Here's my du factor. The integral of cos of u du is sine of u. So it will be minus 1/12 sine of 6x. And now we can add our constant of integration. So using that identity allowed me to put this integral in a form I could integrate. Let's take a look at an example where we have a power of 3. Again, if I had a factor of sine of x dx, I could integrate this according to my power rule. But because I'm missing sine of x, then I have to do something else. So what I'm going to do is I'm going to break this up as cos squared x times cos x. Now I don't want to replace this with my double angle identity. Instead, I'm going to use my Pythagorean identity. So I'm going to replace cos squared x with 1 minus sine squared x. Now I can distribute this cos x, so it's going to be the integral of cos x minus sine squared x cos x. And if you want to break up the integrals, you can. So that will be the integral of cos x dx minus the integral of sine squared x cos x dx. Because I'm going to have different patterns of integration. This is just simply cos of u du. So the integral of cos of x dx will just be sine of x. In this case, the pattern I'm going to use is u to the n, where u is sine of x, the du factor is cos of x dx. So I have my du factor. So I'm going to use my general power formula. So my integral will be minus 1 over n plus 1, so 1/3, the function to the n plus 1 plus c. So depending on what the power is, you're going to use different identities. Let's look at 2 more examples to help you understand. In this question, I have sine of x to the power of 4. So I'm going to break that up into sine squared x times sine squared x. Now this is different than the last example. If I just had a sine x here, if this was a cube, I would just have a sine x. I would use my Pythagorean identity. But in this case, we have squares on both of them. So I'm going to replace them with the double angle identity. So it's going to be 1/2 minus 1/2 cos of 2x times 1/2 minus 1/2 cos of 2x. Now I'm going to FOIL this. So 1/2 times 1/2 is 1/4. I will have minus a negative 1/4 cos 2x minus 1/4 cos 2x, which would be 2/4 cos 2x, which is 1/2 cos 2x. Negative times negative gives me positive. 1/2 times 1/2 is 1/4. Cos of 2x times cos of 2x would be cos squared of 2x. Now I'm going to be able to break this up. So I'm going to have the integral of 1/4 dx minus, we can pull that 1/2 out if you prefer, integral of cos 2x dx, plus we can bring that 1/4 out, integral of cos squared 2x dx. We know how to integrate these 2 terms. The integral of 1/4 dx will be 1/4 x minus, this is just simply cos of u, where u is 2x. So the du factor is 2 dx. So I need to multiply by 2, and I also need to divide by 2. So now I have the du factor there. I can integrate that. So it will be 1/4. The integral of cos of u du is sine of u. But I'm stuck with this term. I need to use my double angle identity again with this because I can't integrate when it's squared. So it's going to be 1/4. And then cos squared of 2x will be 1/2 plus 1/2 cos of double that angle, 4x. So this is just what I had on the board. Now we have to integrate this. So I'm going to break this integral up into the 2 terms as well. So this will be equal to 1/4 x minus 1/4 sine 2x plus 1/4 times the integral of 1/2 dx plus 1/4, I can bring that 1/2 out if I want, times cos of 4x dx. So that's going to be 1/4 x minus 1/4 sine of 2x plus 1/4 times the integral of 1/2 dx will be 1/2 x. So 1/4 times 1/2 will be 1/8 x plus 1/8 times the integral of cos of 4x dx. Now this fits our pattern of cos of u. Now u is 4x. So du will be 4 dx. So I need a 4 here. I balance that with a 1/4 there. Now that my du factor is exact, I can integrate this. I'm going to combine 1/4 x plus 1/8 x, which is 2/8 plus 1/8, which would be 3/8 x minus 1/4 sine of 2x plus 1/32 times the integral of cos of u du will be sine of u. I'll add my plus c at the end. So there's lots of steps using these identities and knowing which identities to use. Let's look at one last example. In this example, we have the cos of x to the power of 5. So what I'm going to do is split that up into cos to the 4th power of x times cos of x. Now this is going to end up being part of my du factor, so I'm going to leave that alone. But with this, I'm going to divide this into cos squared x times cos squared x. In this case, I'm not going to use my double angle identities. I'm going to use my Pythagorean. Once you have this factor there, so in other words, when the power is odd, you're going to be using your Pythagorean identities. So this will be 1 minus sine squared x times 1 minus sine squared x. I'm going to FOIL this, so I'll have 1 minus 2 sine squared x plus sine to the 4th power of x. I don't have to do any other manipulation because I have this factor here. I'm going to just distribute that to each term. I'm going to break this integral up. So it'll be the integral of 1 cos x dx minus, I can bring that 2 out, the integral of sine squared x cos x dx plus the integral of sine to the 4th power of x cos x dx. Now let's integrate each term. So my first integral fits the pattern cos of u. So there's my du factor. That integral is simply sine of x minus. Now in this case, the pattern we're going to use is u to the n. So u is sine of x. So the du factor will be the cos of x dx, which I have. So I go back and use my general power formula. So it will be 2 times 1 over n plus 1. N is 2, so n plus 1 is 3. So it'll be 2/3 sine of x to the power of 3 plus. My next term, I do exactly the same thing. I have a u to the n. My u is still sine of x, so my du factor is cos of x dx, which I have. So I use my general power formula on that term. So the integral will be 1 over n plus 1. N plus 1 will be 4 plus 1, so it'll be 5. The sine of x to the power of 5. And now we can add our constant of integration. These types of integrals involve lots of work. The higher the power, the more steps are involved. Practice questions similar to this where you're working with sine and cosine and having to do the manipulation using either your Pythagorean identities or your double angle identities. The next video is going to be similar, but we're going to be using the tangent and secant functions, but we're also going to be using some identities. So once you're ready, I'll see you then. Take care.